Hi folks and welcome back. So since my first porous materials tutorial, a bunch of people have been asking how to make their own specific geometry porous, not just primitives like cubes. So here we go, porous materials part 2. Let's turn any geometry into a porous structure. So to illustrate this setup, I'm going to be using a Suzanne, just as an example mesh. So go ahead and add a monkey head, Shift A, mesh, monkey. To give it enough geometry for the operations later, I'm just going to add a subdivision surface, and I'm just going to go ahead and apply that straight away. Next, let's open up geometry nodes. This is essentially what we had before. Go ahead and pause this screen to create this node setup. If you want to understand what's happening in more detail, I suggest you check out the first tutorial. But the TLDR, the main ingredient is this volume cube, and we're piping in a texture, in this case a Voronoi texture, to drive the density so that it has spatial variation to create all of this porosity in the material. So to make this work for any object, we need to add a few edits. So the way we're going to do this is we're going to have our volume cube fit around whatever object we want. Then we're going to cut out all of the volume inside of the mesh and then convert what's left into the porous material. So step 1, we basically need this volume cube to adjust in size to accommodate for whatever input geometry we give it. The idea is we want to create a bounding volume cube. So to do that, from the group input, look for a bounding box. And now you want to apply the minimum to the minimum of the volume cube and the maximum to the maximum of the volume cube. And now the size of the volume cube should match exactly the size of the input geometry. You can see what's happening if we just join the input geometry with this new adjusted volume cube. So here's our Suzanne. And if I go ahead and transform Suzanne around, you can see that this surrounding volume cube adjusts in size all the time so that Suzanne fits perfectly inside at all times. The next step, basically, we want to cull away all of this volume outside of Suzanne. So to do that, we need a way to compute volume inside versus outside of a mesh. Here's how we're going to do this. We have a mesh surface sitting inside a volume. For every position in the volume, we want to find the nearest point on our mesh surface. We then compute the vector between the volume point and the mesh point. Let's call this vector R. We also want to find the normal vector at that nearest mesh point. I'm going to call N. And we're going to evaluate the dot product between R and N. If the volume point is inside of the mesh, the angle between the vectors should be less than 90 degrees, whereas if the volume point is outside, it'll be more than 90 degrees. So by taking the dot product, we have this kind of relationship here, where the dot product should be greater than 0 if the volume is inside of the mesh, and it should be less than 0 if it's outside of the mesh. So let's go ahead and make this using nodes. Let's add a position node, a geometry proximity, and a vector math node. This is going to give us positions of our volume cube because it's evaluating the context of the volume cube. Now to find the nearest point on the surface of our mesh, plug in our input geometry into the target socket. Our source position is the position of our volume. So go ahead and plug position into source position and change the target geometry to points. Now our output position is the position of this nearest point on the mesh surface, and we want to take the difference between that and the volume point. So set the vector math to subtract, and subtract the output of the geometry proximity with the position node. So now this gives us our R vector, the vector joining the volume position with the nearest mesh surface point. So I'm going to frame these and just call this our R vector. Next, we need to find the corresponding surface normal vector at this nearest point. For that, add a sample index, sample nearest, and a normal node. Again, connect the input geometry into the geometry inputs for the sample index and sample nearest. Now we want to sample the normal at the nearest position that we just evaluated earlier using the geometry proximity. So we want to take that position of the nearest point and plug it into sample position. And now the output index should be the corresponding index at that nearest position. And we want to pass that into the index value for the sample index. Change the value type to vector. And what we want to do is say evaluate the normal at that nearest point. And so that gives us our N vector. I'll just call it the normal vector. So now we have our R vector and our normal vector, and we need to take the dot product. So go ahead and add a vector math node. Set it to dot product and take our R vector, our normal vector, and now we want to compare, and we want to say As before, if the dot product is greater than 0, this should identify volume points inside of the mesh. I now want to plug this into the density of our volume cube, so I'm going to shift all of these nodes to the side. I'm going to take our map range node from our original setup and plug the greater than result into the input, untick clamp, but go ahead and plug that into the density. And now we're trimming the volume so that there's only volume inside of Suzanne. If I get rid of Suzanne by just disconnecting the input geometry from the join geometry, there we have volume in the shape of Suzanne. So we've cropped our volume. We now want to apply all of the stuff from before to make it porous, and we want to do that before this greater than gets piped into the map range. So we want an additional condition applied to the density input to look for a Boolean math node. And I want to say where the volume is inside and abiding by this texture of the porosity. Now if I pipe that into the map range instead, we can bring up the color ramp as before. You can see it's a little bit slow, but we're starting to get porosity inside of our volume, just like before. As always, volume effects are quite computationally challenging, so I would recommend keeping the resolution count of the volume cube to something low while you're working. So I'm going to set this to 64. And now all that's left to do is just to convert this volume back to a mesh. So delete this join geometry and just connect back the volume to mesh, set shade smooth, and set material back into place. And so there we have porosity going. I'm going to set the volume to mesh type to amount. As you increase the resolution by changing the resolution of the volume cube or the voxel amount here, you might start to see some weird faceting artifacts. And that's basically where the volume has been cropped. So these kind of ridge effects here. And if you want to smooth these out, you just apply non-zero adaptivity. And I'm going to set this to something quite high, like 0.95. And that basically makes the volume surface adapt a bit more. And so go ahead and play with that to smooth out the features of any stepped artifacts, basically. And so now the same controls as before apply. Change the scale of your noise, your color ramp, and you'll get different porosity effects going. Equally, you can change out this Voronoi texture for other types of texture to get the porosity effect that you want. Anyway, this porous materials node is now ready for you to use. So go ahead and try applying it to your own geometries. And that's it for this video. If you enjoyed it and found it useful, please leave a like and a comment as always. Subscribe for more tutorials like this, and I will see you all next time. Bye bye for now.